Hi and welcome for today's seminar. Today we have our employee at LunaX and also part of Sintera Group, Raf Baliot. A little bit about Raf. He's a machine learning engineer with more than 10 years of experience in deep learning, machine learning, and software engineering. And he promised you a seminar with a lot of enlightening experience. So today's seminar will be about pedestrian mapping from electrical scooters through computer vision. So that's it's about exploring different ways of mapping out the locations of pedestrian around the electric scooters using a forward-facing camera. So welcome, Raf, and I will give you the mic so you can start to maybe a little bit about yourself and then present the seminar. Thank you.
Yeah, thank you, Michael, for that good introduction. So I'm Raf, as Michael said, working for LunaX under Syntheta Group. Been working in the machine learning space for around 10 years. So so I will share one of the projects that we've worked with with the customer as well as Vinova. I'm sharing my screen. Hopefully everyone can see it. So this is part of the eSafe project. So we would like to understand the behavior of e-scooter riders, and through that we use a forward-facing camera as well as different kinds of sensors. So I would present a part of the study that we did, but the whole study is available also on the Vinova website. So if you're more interested about knowing about the insights that me and my colleague has done, so feel free to visit the Vinova website. So yeah, so I would walk through some of the things that we've done. So we've done some gesture classification, and then we've done some pedestrian detection, pedestrian tracking, and then we performed some depth estimation to get the distance. And then we had some problems with the forward-facing camera that I will show you as we go through the slides. And then through that, we have some angle compensation algorithm to make the camera a bit more stable. So so let's start with the gesture classification. So here, what we were trying to do is, uh, we have the camera moving forward, and it's a fisheye camera, and we can see the hand movements of the riders, and then we would like to draw some conclusions from it. So let's start first with the research background. So why are we working on gesture detection? How does it relate to the project? And so this is what our idea when we are given the project, right? So you can see these are the samples of the camera that we have. So it's a fisheye lens, so you can see the top, but you can see the hand. So we are curious to see if the handlebar interaction would provide us a little bit more about the rider. So for example, when we watch some of the videos that we were able to gather, so you can see that there are certain scenarios in which the handlebar interaction is a bit different. So, for example, here on the top left, so it's just a person who's pushing the e-scooter with one hand. On the right side, you have someone who is braking before a turn, and then on the bottom, you also have some sort of collision accident or close to a collision accident in which the rider is trying to break through, and then mostly when people are riding on very high speed across a very empty road, then you see that people tend to hold on to the handlebars really tight. So it's our idea. Hopefully we're working on an algorithm to capture this behavior automatically rather than watching all the videos one by one. So we would like to define a problem. So from the research idea that we have, so we have a very simple problem. If the hands are visible to the camera, so we would like to identify it into three different labels. So is it not in the handlebar, is it in the handlebar, or is it touching the brake lever? So From that, so we have a lot of videos, and then we would talk more about the video processing. How did we process our data to solve the issue? So first, uh, we would like to convert the problem into an image classification problem, and for that, we would like to extract the keyframes. So if you're not familiar, so in a video you have the keyframes, which are the frames with the most information. So these are frames that actually exist rather than transitionary artifacts that you see through a video. So by allowing us to convert a video into the several keyframes, it allows us to change the problem into processing a lot of videos into processing a single image, which allow us to come up with a very fast algorithm that could run actually real time. So and then after we have the keyframes, so what we did was we extract the keyframes. So when we watch the videos that we have, so we notice that uh the camera won't always be aligned. Sometimes it's a bit shifted to the left, sometimes it's a bit shifted to the right. But the location of the handlebar and the hands would always fall into the top two quadrants. And so we started with the idea that rather than working with uh, a problem or using a model that would also provide the location, for here we just assumed that we would always get the hand and the gesture into the top two locations. So that also allowed us to simplify the models that we could use for the detection. And then the bottom two, since they are mostly on the road, so we just discarded these two image. Uh, yes, and then next is that after we've done our uh, splitting of the keyframes, so we actually don't have any labels that exist for this data set. And so we had to go through all of the videos that we have, try to get some samples, and then try to label them manually, which is a bit of a tedious part. But in this case, we actually use a program called Label Studio. So it shows you the image very quickly, and then you just click the result. So that made the labeling a bit more easier. But yeah, there's some label work that we had to do in order to get some data. Then after we have our label data, so we want to classify the keyframes. So we have a machine learning model. So we trained it with the labels that we have, pass the image, pass the labels, and then after a while, we were able to train a VGG model that can predict the result given the quadrants. So yes, and then we will dive a bit more into the machine learning modeling that we perform, a bit more about the details. So we created first from the data set. So when we have the data pre-processing pipeline that I mentioned earlier, so we apply this to all of the videos that we have available labels for. And then from there, we split this different videos into a different data set. So for example, all of the keyframes from the trained video would only be assigned to a trained data set. If the video is assigned to a validation, then all of the keyframes from that video would only fall also to the same set. So the idea here is that we would like to keep the the correlation between the sets low. So for example, if you have different frames from a different video, since a video, when you capture a video, there's not a lot of change unless you quickly turn the camera. So it means the frames in a certain video, they have very high correlation, or they are very similar with each other. And that's something that we would like to avoid. So we would like to challenge the model to be able to learn from the frames from different videos. So we don't want to introduce some bias to it, so that we are sure that the models that we have are robust and they can generalize properly. So yeah, and then once we have the data set, so we also have uh, an additional pre-processing pipeline, but this is more into for us to be able to feed the data set that we have to the model. So we have an original image, which is 360 by 266, and then we try to resize it into a square, 256 by 256, and then we normalize the model intensities or the pixel values into 0 to 1. So just to make sure that when we feed the model, the images that we have to the model, so the gradients would be stable and we would be able to train really well. Uh, and then we also perform a very quick and very simple data augmentation. So once we have the data pre-processed, so we just try to introduce some basic transformation. So for here, we could go a bit more about adding noise and adding contrast and so on, but at least on the models that we did for the research paper, so we only did flip image and rotational image. So the motivation for this is sometimes the frames that we would get from the videos are not very centered. So you can have a hand that is a bit more on the edge or a hand that is a bit more on the center because the camera itself is not perfectly centered for all of the e-scooters that we have. And so uh, introducing these rotations kind of compensates for those scenarios that we encounter in real life. Uh, yes, and then after that, so we have a train model. So we train this on a VGG model that is pre-trained on ImageNet. So from the VGG 16 model, so we lock the weights for the earlier layers, and then we only keep the last 4 layers trainable. And then we also added the 3 custom layers to be able to focus on the image problem that we have. So you can see at the end, it has 3 labels, which is what we are focusing on, detecting, no hands, there's a hands, or if it's pushing the brake lever. And then we were able to get 93% accuracy on all of the 3 classes that we have. So which is for the experiments that we did, we feel was good enough after we run it through all of the videos and presented our conclusions on the actual paper. So yeah, so so that's the work that we've done in gesture detection, trying to see the behaviors of the different riders as they drive through the roads of Gothenburg. And then now we would go through some of the work that we've done into pedestrian detection. So again, we would go to the research background just to see why are we doing this. So in order for us to detect the interaction with the pedestrian, so we first need to identify from a video, where is actually the pedestrian. Otherwise, we cannot really derive some conclusions from it. So uh, yeah, so the first things first is to know where they are, and then given that pedestrians are basically people, and in a lot of data set that exist for object detection, there's always people in there. There are actually even a lot of pre-trained models that are very focused on pedestrian detection, which later we would go through as well. So rather than training data and because at the end of the day, if we would like to get some data for pedestrian detection, we would probably use existing data available on the internet, which most of the existing pre-trained data are already trained upon. And so we didn't really go deep into the object detection concept. So we would just like to explore existing pre-trained solutions and see if this would work, or maybe in the end we would need to train them anyway. But at least when we perform the research study, we kind of come to a conclusion that they are good enough for us to get some valuable data and conclusion for the research that we are doing. So yeah, so here basically the main goals is that we would like to reuse the data. People have pre-trained the data on these models already. Then we don't need to train. There's less training time, if any at all. And then we don't even need to have label data if we would use out of the box solutions. So we would go to the model selection. So we would just show some of the models that we tried and what's the result, some of the comments that we have on why we didn't work with it, why we didn't choose it, or you know. So what are these other models provide, basically? And so here we have a TensorFlow object detection module. So they provide uh, what you call this, an object detection library and an object detection model zoo. A model zoo means they provide a lot of models that other people can use to start with. So when we were working on this project, so it's still a valid option, but as I worked through the presentation, so they currently deprecated the whole library, so meaning they now stop recommending people to use it. And in some ways, it's a bit visible to the results that we got. So it missed a lot of detection, even though it was trained on a Kitty dataset. So it's a dataset that is used for autonomous driving. So you can see, for example, on the image on the right, the top right, is that it's missing the. It was able to detect the cars on the left, but not the cars on the right. And on the top left, you can see it was able to detect the car, but not the car in the center. And then it in our examples, it mostly really fails on all of the pedestrian detection, which we are really concerned about. So, uh, but yeah, this is what is available in TensorFlow library, and we feel it's something that is easy to try, but unfortunately didn't work out for us. And then we also have this urban project detection. So it's a project that they've done in Montreal, in Canada, in which they have different traffic cameras, and then they would like to see which if there are pedestrians, if there are other objects. So they would like to focus on the city area, what objects you can find in cities, and then try to see if it's something that they could use for the city. Uh, and then unfortunately, it may have been something to do with the type of camera that we're using. It's pretty good in detecting some of the vehicles. It was also able to predict some of the pedestrians, but it always has this issue where if you look at the images on the left, so you can see that it always try to count the box that we have on the image that we have as some sort of detections. And it may be related to how they train the model, because they trained it on traffic cameras. On the other hand, we have fish islands. And aside from the distortion, there's also a boundary that we can see from the videos. And it's causing some problems with the detection. So ideally, when you have this detection, so you could increase the threshold or decrease the threshold of the models to play with this false positives. But what we found out is that for this model, even though it's detecting objects outside the actual camera, so it's giving very high confidence. So it was hard for us to utilize the model. And then we have this YOLO P, which they said it's a version of YOLO for driving. And then initially we thought that this would be a good model for us to use, because we feel like when you're driving, you should be able to take note of pedestrians. But once we tried it, we realized that the model is only caring about the vehicle, so it doesn't really predict the pedestrians. So it was performing really well though, but unfortunately, uh, it was not able to satisfy our criteria. But one of the things that we also, one of the reasons why we also tried it was because we were also looking a bit far ahead. That maybe in the future we would do some uh, processing with the e-scooter riders to the vehicles on the road. So that's why we feel it's fine to present the result. Uh, yeah, and then we have the Pedestrian, which they say it's a model that is really focused on detecting pedestrians. And I would say it's really good at detecting pedestrians if they are walking. So there are, how do I say this? So this pedestrian symbols, the one with two people walking. So they're very good at predicting people in that scenario. But when it comes, for example, if you look at the bottom left, so on the bottom right, on the top left, you can see that it detects the person, but on the bottom left, you can see it doesn't because it's people started to ride the e-scooters, and this is also something that you can see when you look at people on a bike because when you're cycling, you don't have the same posture as a walking person, so it also miss those detections. So in some ways it's really good at the pedestrian detection, but it doesn't work that well on other kinds of people that are sharing the road, I guess. And then a minor issue is that some of the shadows are being detected. So uh, and then on the last we have YOLO version 7. So overall it has a great performance, but still has some issues. Formally, not formally, but specifically on the hand. So it's detecting the handlebar with some sort of label, and so it gets some partial detections around the edges. But for this case, it was a bit easy for us to just clip the top part of the image since under normal conditions there would be no pedestrian on the skies. So we feel like it's fine to just remove those. And then yeah, so at the end of the day, we went with the YOLO 7 performance due to its performance. I mean, and then uh, so the YOLO family of models has evolved throughout the years. And one of the advantages also for the YOLO models is that it only looks once, which means that compared to the other algorithms during its time, so it only has to do the prediction once. So the reason why YOLO is named YOLO because once it reads the image, so it provides the location together with the classification, meaning whether it's an object, whether it's a person, whether it's a car. So it does it in a single pass. So it means you get the result very quick. And so for us who would process a lot of data, so using the YOLO also provides us that uplift in inference performance that we would really like to have. So yeah, so at the end of the day, so we settled with the YOLO model and use it to work on our pedestrian or people detection algorithm. So, and then, so now that we have the pedestrian, so for each frames that we have, we know that where the pedestrian is, but, and then we could always say, where are they? But then how do we know that the person from the previous frame is the same as the person on the next frame? Right? So we would also like to have some sort of temporal information that we could connect the different frames to see, okay, this person is the same person, so that we could sort of create a map in which, okay, this person is moving to the left, right? Or this person is moving behind an e-scooter, or the e-scooter is moving fast towards a single person. Uh, so then we'll look at the research background. And so, yeah, so as I mentioned, so we would like to associate the object detection into an entity. So if you look at the image of the example that we have, so you can see here we made some basic illustration. So for example, the truck, so you can see the truck, there's a line. So it means initially the truck was actually on the right side of the e-scooter before it come to this side. And then you can see the persons also have lines when we have detection. So, and then you can also see, aside from the lines, the labels that we have also include an identifier. So normally, if you predict or if you look at samples of object detection, so you would just see if it's a person, if it's a truck. But you can see here we're also adding an ID, so it means that number 11 would always be the same, right? So those are our tracking ID. So the idea is that we could use this to create some sort of more conclusions towards how people are moving around e-scooters. And so, yeah, so for this, we focus on an algorithm named sort. So sort, the big advantage of sort is also the performance. It's really fast. It's based on very simple algorithms. There's a lot more upgraded versions of sort that exist at the moment. But given that we would like to run through a lot of data and a lot of videos, so we are again optimizing on the performance. So sort stands for simple online and real-time tracking. So I'm not the one who made that meaning, but that's what it means. And then the sort has two main algorithms, or it has two main components to its algorithm. One is location prediction, and one is cost allocation. So here on the image on the right, so we have the sort flow. So you can see that we have this yellow greenish uh, frame, and let's call this the initial frame or the frame t minus one. So what sort would do is that it would take this initial frames, and then once it knows the location of the initial frame, so it would try to make a guess. So if this object is moving, where would it be on the next frame? So, and of course, the prediction will not be 100% correct, right? It will be off by a bit, as you can see in this example. And so of a frame, it predicted it has a prediction for the image to be on the upper right, but then the real next frame represented by the blue box is on the lower right. And so what sort does is that, okay, now we have some predictions as identified by this dotted box. So we know that it's not going to be perfect. We know it's going to be wrong. But if that's the case, which which box is it the closest to, right? So even if we have this dotted box here, even if it's a bit far from this frame, but the other option is to be on, on the frame on the very far right. So given our distance metric or our overlapping metric, so our cost allocation would say, yeah, this prediction is not good enough, but it's better than the other prediction, and probably this image or this prediction is wrong, and we just assign it to the closest one. So that's basically how sorts work. The sort algorithm works. So you have allocation prediction, and then from that prediction, it would try to look at the next frame and try to see, okay, this may not be the best prediction, but to which new objects is it the closest to? So that's a short background of the algorithm. And then It does the location prediction through what they call a Kalman filter. And to make this prediction, so it uses the center of the box as well as the area as well as the aspect ratio. And then since we're looking at a temporal movement through time through different frames, so we also look at the velocity. And we also have the change in area. So the idea is that as you move through the image, of course, if you move forward or backward, the area of your what you call this, the area of the box would also change, because when you look at the image, the smaller the image, sometimes it means the farther it is, and then the closer the image, uh you get the larger image when it's closer. So I won't go through very deep in detail on how a Kalman filter works, but it's an iterative prediction algorithm. So it means that you would initialize it, and then you would make prediction, and then that prediction would be wrong, and then after you make your prediction, so you would make a measurement, right? So from a short perspective, you have your frame, you make prediction, and then after your prediction, you get the actual frames, right? And then you do some cost allocation, and then the new assigned would be called the measurement. So it means now you know what's the real value, and then you could see, okay, maybe I'm wrong by 10 pixels by 20 pixels. Maybe I'm wrong by this amount of pixels. And then in the Kalman filter, we also have the fusion, in which, okay, now we see how much errors did we have. So can we use the new prediction to make the next predictions better? And so it's similar to how we do with the video, in which every new frame that we get a new prediction, and then it means that the tracking that we have also gets better as we associate the same objects for multiple frames, because we have this loop of a prediction, measurement, and fusion or correction. So that's how the Kalman filter works as part of the sort algorithm. Then we also have the Hungarian algorithm. So I won't also go through in detail on how the Hungarian algorithm works, but for the Hungarian algorithm, so we use the overlap as the cost, or the IOU. So meaning, if you look at the different boxes, so they should have some sort of overlap for them to be assigned to each other, and then the one with the maximum overlap to the prediction will be the one who's assigned, or may not be the maximum depending on how the Hungarian algorithm works. And then on the sort algorithm, they also define a minimum IOU. So sometimes you could say, okay, if the overlap is pretty small, I don't want to allocate this boxes to it. So I want to have some sort of a minimum threshold. So Hungarian algorithm, it's basically an algorithm if you have two sets of objects. So here we have the reds and the blues, and then let's say the lines have some sort of cost into it. They have some weights, they have some measurements. And so the Hungarian algorithm will try to find out uh, what would be the optimal way for you to assign uh, by accounting the cost. So that's basically how it works. So it works through some subtractions and so on and so forth for you to get to zero out some of the values. And then if it doesn't work, then there's a new rule that you need to follow. If that doesn't work, then there's another rule that you have to follow, until at the end it would converge, and it would say, okay, this red should be into this blue, this red should be into this blue, and so on and so forth. So yeah. So now that we have that we are able to track the pedestrians, and then we were able to associate them to different entities. So we know now how they move through time. So now we would like to know, okay, how far are they from the e-scooters that we have? Because then yeah, we know that some people are moving around us, but we don't know how far are they. And so we have a research problem in which we want to estimate the distance between the riders and the pedestrians. So here you could see some sort of drawing that we got from our e-scooter partner who has allowed us to install this cameras. And so unfortunately, so these are the only measurements that we got. So we were not able to have access to the actual scooters and play around it and maybe get more measurements. So these are the only ones we need to work with. So initially, we would like to explore a lot of depth estimation models. So and you can see how they work. So you have an image, it would try to present some sort of depth estimate. So the bluer the color, the closer it is. So these are different models that were available uh, for us when we were working on the research. And so this would allow us to, to have some mapping to see, okay, maybe the pedestrian is a bit blue, then it means it's closer to us. The pedestrian is a bit yellow, so it means it's far from us. So these are the models that we explored. So the one that we really put a lot of focus on is Adabins. I think now TikTok also has its own model that is trained on more data. So that's something that we haven't checked. But so visually, we feel like the results make sense, from a visual perspective. So you see, for example, on the top, so you have the rider, another e-scooter rider. It's a bit darker in color compared to like the buildings, which are a bit more light in color, meaning they are farther. You could also see this on the bottom example. So we have a rider as well on in front of us, and it's darker as well compared to the horizon, to the buildings. Uh, but we also have some issues. So one is the sky and horizons are black out, which for us doesn't really matter that much since we doubt we would be able to find some pedestrians flying around. So but the issue that we really had was that when we tried to relate the image that I showed before that we got from the scooter company, so it doesn't match up to the distances that we get. So it could be that because we are using a fisheye camera and the model is trained on flat, rectangular cameras, the normal cameras that we have, and so it could be that the mapping of the distances also doesn't make sense. And so from here we decided that maybe we should go with an analytical approach. So uh, one of the things that we have is that we feel like we don't have the model, that we don't have the model, or we don't have enough data to train a model, given that we only get, I believe we have 16 points and it's one for each angle and one for each distance. And we cannot really benchmark the data since we don't really have access to the camera. And so we feel like, okay, these are the data that we have, and we would try to make most of what we have. Uh, these are the actual instrumented scooters that we have. So if you ride something like this in Gothenburg, then yeah, we know where you are. Just kidding. Yeah. So these are the available data that we have mapped to the sample video that we were showing. So we only have the 15 points. And then of course, for example, you could already see where it breaks down, right? So here you can see that the e-scooter is a bit tilted. And of course, it means that the measurements that we have is also affected, but we have to work with what we have. So we try to work with this data. So the idea that we have is, okay, so we don't have data, but there's some sort of shape that we could see throughout this these points. And so what if we try to estimate an angle as some sort of a family of ellipses, and then we try to just interpolate it with the points that we got from Voy, and you can see the plot on the right, it looks fine. But at the end of the day, we actually just focus on the central angles because we feel like the edge angles are a bit noisy because it's basically extrapolated angles. But and then for the distance, we measured it as some sort of a family of hyperbola. So you can see that there's a yellow section, which is like the negative section because it's harder than the wheel, and then we have some lines that shows us some distance in meters, and then the top of the horizon is invalid because it's pretty much the sky, and we feel like at least for our research scope, those would be invalid data. So yeah, so that's basically how we come up with the measurements. And then I would show you some of the samples here once we talk about angle compensation, because you would also see why we are doing this angle compensation thing. So let's go to the research background. So these are the scooters that we have, and you can see how we have the sensors. So it's not perfect. It's not perfectly horizontal. And then another issue is that if you can see the modules are attached on the handlebar, the I don't know how to call it, but the bar that where the handlebar is attached to. And so it means that when we turn the e-scooter, the camera also turns. So it means we get some, the focus changes when we turn, even though we're still driving forward. And so I have some sample issues here. So you can see that we're driving forward, and you can see that once you move, the steering wheel a bit, if you're estimating the location from the camera perspective, so it looks like the person in front is moving, but it's not actually moving. It's just handlebar that is moving, right? And so this caused a lot of issues when we're trying to detect data, because then we would see that all of the objects will just shift, and then it's like, what's happening? And then it is the camera that is moving, not the world. So, but from the camera's perspective, it's the world that's moving. So, oops. Then, so to correct that, we look at the concept of optical flow. So optical flow, okay. So optical flow starts with looking at the corners. So we call it like point of interest selection. So the concept of corners in computer vision is that these are the points in which there's a lot of difference towards the surrounding area. So, for example, if you look at a point inside the square, so it's the same color as the the pixels around it, and so we cannot say it's a corner. But when we look at the corners identified by OpenTV, so you can see that uh, they're around the white part of the image, because there's a lot of difference between the colored part and the white part. And so when you ask OpenTV for a corner, or also called point of interest, so it would give you this edges. And then once we have this point of interest, so we go with the optical flow. So the idea is that you have a point here, and then it would move. And so what you're saying is that the pixel values for this point could now be the same as the pixel values for this point, right? Because if this object moves here, then if this is a red dot that moves here, then this should also be a red dot. And so what we do here is that in the Lucas Canada method is that we try to look at the surroundings and say, okay, I have this is the starting point. I look at the surrounding box, right? It's up to you to define how large that box is, but you would say, okay, this point can only move around this box. I would check where is this point similar to the surrounding images. And that works really well. So the only disadvantage is that it only works with small movements, because if this circle move outside the box, then it means you cannot identify it, right? So you only identify it until you're the box that you're looking at, the neighbors that you're looking at. And so to remedy that solution, so we actually do a pyramid method. So it means that if you have, let's say, a 500 by 500 image, so you maybe convert it to, let's say, a 125 by 125, and then you run the algorithm here. But then now, since you're looking at a very small image, so you could capture the whole image with a very small number of pixels. And then, since it's a low resolution image, so you say, okay, but this is only my estimate. And then you try to run it on the next resolution. And then now you could refine your uh, optical flow results. So you basically do some iterative results in order to improve the performance. So you start with a low resolution image, and then you go farther to a higher resolution image. And then turn compensation. So once you have optical flow, so the idea is that you would get some points, and then you also now know the movement. So as an example in this image, you can see there's a lot of arrows. So it identifies all of the optical flow, and then you compute the angle of the points based on the points that we have, and then we compute the angle on the flow, and then we use the median. So since we get a lot of flow from a certain image, so we just use the median to do the adjustment, and then these are the results. So this is the same example as we have before. So you can see the top we have the original projections. We have the without the optical flow, and then on the bottom we have like optical flow stabilized. And then if you run the video, so you can see there's some sort of big shift on the top one when you turn, and then you can see it's not present on the bottom one. It's a bit more stable. So from here we feel like it was able to compensate for the drift a bit. But when we watch like longer videos, so our angle estimation and distance estimation still drifts apart when we have very long videos. And it could be through a lot of reasons. So it could actually be our angle calculations are not perfect given the sample of data that we have. It could also be related to the bounding boxes, since we use that as a way to detect the image, or it could be because our turn compensation is not good enough. Though we feel it's still better than not having it. So yeah. Oops, sorry. Then here we just have the full video for people to see. So as an example, so you can see there's a person riding, and then you can see we're moving forward and then to the right. And so it makes sense that the person would be on the right, but then it comes to 180 degrees. So there's some sort of drift towards making a very accurate global estimate of the actual locations, because the turns, if you look at the driving path, it doesn't make sense with the angle paths that we got. So we're not there yet when it comes to fully estimating trips and mapping out how they work in very long distances. But that's what we have. And then I think I take uh, quite a bit of time. So is there any questions that people would like to ask about the research project that we did?
Yes, thank you, Raf. Thank you very much. Really interesting seminar. I did my research pretty early 20s, and the first algorithm I did with optical flow was Lucas Canade
Oh,
algorithm, and we were optimizing it for lip movement.
uh-huh.
So I recognize a lot of things that you are now talking about, computer vision. It's really nice to hear about it. So from here, I have some questions, but if there are anyone else,
Yes.
yeah. So would you like to come forward and just
Raf, can you hear me?
Yeah.
Thanks for a very nice presentation, very clear as well. Uh, just so I was wondering, so you all the data that you take is from the scooter, right? So from the
Yes.
so I was the last part it was not very clear to me, but do you use the speed of the scooter to correct when you do the tracking, or it's just
Uh, yeah. No, no, not yet.
the source of the camera? It's also moving, so you have to correct it, right? To
Yeah. So we have one of my colleagues who tried to do some estimates using the speed and then the GPS, and then we also tried to see if so he tried to calculate if you can actually determine the turning angle based on the speed and so on. And then we tried it out, but there was also some large variance when it comes to the estimated values that they computed. And so when we actually run it, it actually performed worse. So it may be that there's something that we haven't tried on that area, but so far when we tried it, given the time that we had, it didn't perform as well as we would like it to be, unfortunately. So
so can you clarify to me? So, for instance, if I have a standing pedestrian and you are moving very quickly, so the two frames, the t minus one and they will be moving, right? So and then
no?
if you're not taking into account the
They are not moving. It's you have the image, so of course the pedestrian distance will change,
yeah,
but the image is there. So you don't need
but
any.
but the two frames
Yeah,
if you're standing
yeah,
in your scooter,
yes,
the frame will be in the same place. But if you're moving with your scooter, the frame it's like the pedestrian is moving.
exactly. It's the same case if the pedestrian moving or the scooter is moving. So you have the case is still the same. So you
But
have always a movement.
you always you don't distinguish the two cases.
No,
yeah, no, no,
maybe.
yeah, that's correct. Yeah, we don't
Understand?
distinguish the K.
Okay.
Yeah.
But as you said, we could use the distance to see if it's a movement induced by the e-scooter. But we haven't really gone far to that step.
I have maybe a related question about that calculation. So in your, if you understand correctly, you estimate the depth only with one frame. So it's a static measurement. You're not using the.
That's another question because the optical flow is just
Yeah,
uh, the stabilization of the movement. I mean, the scooter, the image, but the distance. I think that was another part, which is they didn't. Or I don't know.
Yeah,
You did you succeed to measure
yeah,
the distance?
yeah. So so the thing is we don't have access to the e-scooters physically, and so we only got like 15 points from the e-scooter manufacturer that oh we take one picture, these are the points and the pixels, and then so we just try to map it out using some analytical method, using some families of ellipses and hyperbolas. So we
that you
only get the distance on the
right,
single
right.
frame.
Okay. No, I was just you probably have a very large uncertainty for instance because you measure like where did the box touch the floor, no? So if
Yes,
someone is
yes.
holding and it's just a small step,
Yeah.
you cannot distinguish what's
I
the
had the same question, yeah, because yeah, even if you have a shadow of yourself, then you
yeah,
don't
it's hard to
yeah,
identify where you were
exactly.
touching.
Yeah, but I have a solution to that. Maybe we should not give it to them. You know, Raf, we have the project Biometrics within Sintera Group, and we have had the same idea of in a conference room where you want to measure the distance during the pandemic was an issue, measure the distance between people. And by using a camera lens, you can simply not do that in an easy way. So the solution was by two stereo camera. If you have
Mm-hmm.
two, by a
Yeah,
stereo, you solve this problem pretty easy.
yeah,
Or as we are doing now is the TOF, which is a small leader system.
yeah.
Then you know the distance more exactly.
But you probably
The
more than
object.
double the cost.
No, it's. I mean, there are simple sensors that you can use.
Yeah.
I have a lot of questions because this is pretty interesting area,
Uh,
but we have only
oh,
three
but
minutes.
just to
I
add
can't.
to your
Yeah,
comment, Michael. So actually, they started another project in this one as an extension, actually, which
yeah,
they call the Microvision project, which would focus more on adding more sensors, actually, since they're also very interested with the results that we had. So now I think they're adding LiDAR and more cameras, a 360 camera, I believe. So
yeah. Very good. I mean, I would like to ask this question, but it's just. I mean, this is a little bit about when you have a camera on a scooter, then you are recording things that are not okay for others. So you have some kind of security ethics into it. Have you been, I mean, studying during this project, this case, or is it just something that?
what's your sorry, do you mean if I'm studying like
No, no,
ethics?
no. During this project, have you touched up on this, like the ethics or security part, where you
Yeah,
record?
so you could see that's also why we try to blur a lot of the faces on
Yeah,
the videos and images that we are presenting,
yeah.
as to not show a lot of very private information. And I think that's also where we would like to automate most of the processing, so that from a research perspective you only see very few of the videos, right? And then it's the algorithm who sees most of it once you are confident that this would work in a lot of cases. So
Yeah. I didn't mean now this research project because in the research it's pretty okay, but coming into a commercial system, then you have been, I mean, you need at least to have an okay from the people that you're recording them.
oh yeah, yeah,
Yeah. So,
definitely.
but that is okay. So I would like to thank you, Raf, now the last minute here again for this nice seminar. And I would like to say that this seminar will be available on our YouTube channel, but also on our webpage, synteda.com. And we have a coming seminar during March that will be also of a big interest, which is hopefully the test and AI. And we have also, as always, follow us at sinteda.com, but also through our LinkedIn channels and YouTube channels. I would like to thank you again, Raf, for a very good, interesting seminar. And we will be, of course, talking and reaching you more. But I would also like to add anyone who would like to talk to Raf can will get the contact information in the video hopefully soon. Okay? Thank you very much, Raf.
Yeah, thank you also for giving me a chance to present the work that I've done.
Thank you. Take care. Bye bye.
Thank you.